Welcome everyone. Welcome to this session. Very warm greetings from Mercy Technologies. So let's see what is our agenda for today. What is our agenda? We'll be learning about recursion. Recursion today. It is a kind of programming. Yesterday we solved two problems using iterative programming. Today we'll be seeing about recursion. Okay. And what is the next agenda? Today also we'll be dealing with factorial program, Fibonacci program, but in a different way of programming that. Okay, yesterday we did that using iterative approach. Today we'll be doing that about a recursive approach. And after dealing these two programs and recursive approach, let's try to calculate the complexity analysis. And at the end, let's try to compare these two approaches, iterative programs or recursive programs. Generally people say like a recursive program, for example, let's say you have so huge big amount of code. If you use recursion, you can reduce that to drastically less number when you use recursive approach instead of using an iterative approach. But is it real? Like, is it the way? Is it correct, etc., etc.? Let's move forward into our today's session and try to find out what exactly it is, right? So let me tell you, let me start. What is recursion? Recursion is nothing but a function calling itself. Let's say you have a function called add, right? You have a function called add. Let's say that function called add is again calling function calling add, then that is called as a recursion. Let me tell you a small example. So here, let's say yesterday we have written some employee test class. In this, what we have done, in the main method we are calling change name, right? In the main method here, the main method is calling change name, which means some different method is calling a different method. But in recursion, the same method will be calling itself, right? The same method will be calling itself. This is the definition, guys. So I think once you're clear with the definition, let's go into coding and understand what exactly it is. Let me repeat it. Recursion is nothing but a function which is calling itself, right? Now, I'll just tell you small simple tips or simple conclusion of yesterday. What we have done is yesterday we have seen two programs, Factorial and Fibonacci series programs. And what was our conclusion? Our conclusion for Factorial was having order of n time complexity, and factorial for Fibonacci series also was having order of n time complexity. So this was an iterative approach. When we spoke about the space complexity yesterday, I told you that if you just go through the code once more, like, we are not consuming any extra space inside our for loops. So that is the reason the space complexity is constant. Whatever is the input that you're giving, how big the n is, it will always be constant. So as per our yesterday's discussion, the Factorial and Fibonacci series programs are having order of n time complexity and order of 1 space complexity, right? So today let's move forward and try to understand what is a factorial program. I'm straight away digging into code, guys. Let me not waste any time. What I told you here, I told you that there is a method, and if it calls that self, then that is called as a recursion. Here there is a method called fact, right? What is it trying to do? It's trying to do something for us. Let's say we are not digging into that right now. This is base condition, right? This is base condition. Leave about that. So what is it doing? There is a method called fact, and inside this method again there is a method called by reducing the number by 1, right? By reducing the number by 1, the same method it is calling again. Okay, it is calling again, right? This is called as a recursion. Let me dig deep into what this code actually is asking you to do. Okay, here again, let me repeat, there is a method called fact, and we are calling that method again in our return statement, right? Where are we calling? We are calling that in our return statement. And as part of our base conditions, we are returning something, right? This is the heart of recursive programming, guys. Recursive programming is nothing but First and foremost, you need to have a base condition for sure. I'll tell you why you need to have a base condition. And at the same time, in the written statement, you will be calling that method again, right? So I'll try to explain that to you in a better fashion. Okay, I think I need to do this one. Okay, so what was our code? Our code was something like this, right? Our code was factorial recursive. Factorial recursive, it's nothing but a method which is calling itself, and we are calling it in our written statement. Yesterday we saw what is a factorial, right? Let me just revise you that statement once more. So here a factorial of 4 means 4 factorial is equal to 4 into 4 minus 1 into 4 minus 2 into 4 minus 3. What is 4 minus 3? 4 minus 3 is 1, right? So when factorial of 1, we already know what is the factorial of 1? It's 1. So that's why here we can stop, because we came to a condition where we already know what is a factorial of it. So similar way, for example, let's say I'm doing it until 1. Here let's say I have a method called fact, and it is calling with the input. I'm just denoting that with f, guys. So there is a method called fact, and we are calling that method with input as 4, right, with the input as 4. So if we see, we are calling this method with the input as 4, and after that we are doing some logic, and we are calling that again with 4 minus 1, which is f of 3, right? F of 3. Again, this f of 3 is calling, after doing something, it is calling f of 2. After doing something, it is calling f of 1, right? It is calling f of 1. So this is the first step in the recursive programming. What is the second step? Second step is returning the computed values to the previously called function. So we know what is the value of f of 1, right? What is the value of f of 1? We are returning 1. So again, what we are doing as part of f of 2, here if we see in the code, we are doing n into fact of n minus 1. So here what is n? 2. 2 into f of n minus 1, which is f of 2 minus 1. It is returning a value called 1, right? 2 into 1 is equal to 2, right? The calculation is done. Now f of 2 and its calculation is done. It's returning its value again. Now it's returning what? It's returning a value. What is its value? Its value is 2, right? It's returning a value of 2. To what? To the calling function. Who called f2? F3 has called the function. Now, as part of f3, what we are doing? We are doing n into, which is 3 into f of n minus 1, which is f of 2. What is its value? It's 2. Then it is 6, right? Again, we are returning the value of f of 3 into f of 4, right? We are returning the value of f of 3 into f of 4. So what is f of 3? F of 3 is 6, which is n into f of n minus 1, which is 4 into f of 3, which is 6, which means 6 4s are 24, right? This is what a factorial is. The factorial of 4 is called as 24. Let me run the program to you and make you understand what exactly it is. Okay, so this is our program. I have given the input as 4. I'm giving the input as 4. Here I'm running the program. What is the answer that I'm getting? I'm getting the answer as 24, right? So what this program is actually doing, it is having a base condition. When f of n is 1, what is it trying to do? It's calling the function again, and at the time of reversal, it is trying to multiply that particular number called n, and it is returning the value at the end. I'll debug this program for you and make you understand what exactly is happening internally, right? This is a very small program. Let's try to understand what's happening internally. So I have put a debug point on line number 8. So here I can see on my right side, there is n is equal to 4, right? The n is equal to 4. So when n is equal to 4, for the first time when it came, let's move forward in our debugging. So what it is doing, it is trying to call the fact again with n is equal to 3, right? What is now the n is equal to 3? Again, it came, it's trying to call the fact method again with n is equal to 2, right? Now it is calling again with n is equal to 1. When n is equal to 1, it is coming to the base condition and now it's returning. Until this point there were method calls, right? Until this point there were method calls. Now we are in the returning call. What is the returning call now saying? The returning call is saying you return 1, and now n is equal to 2, right? N is equal to 3, n is equal to 4. So what's happening in that case? You are returning its value to the previously calling function, and finally you are printing its value. So when you are returning, at the time of return, what you're doing, you're trying to multiply that number with the current number, which the n is, right? Which n is. So by this calculation, it is finally returning a result which is 24, right? Which is 24. This is a small example, guys. And if you see, the only logic in the code that we have written is only this line, right? Only this line. So this is the power of recursion. Only with a single line, it's trying to achieve everything without we knowing, without the programmer knowing. Internally, it is doing something else. I'll come to that in the next part. But this is what the program is, and this is how we are calculating the factorial using a recursive strategy. So this is what it is, guys. Please tell me if you are able to understand what I taught you now. We move forward in my explanation. So with this, what you understood is, this is what a factorial is. So internally, how it is going. Let's see some diagrammatic approach. Factorial. Let's say I'm given something called factorial of 3. What is it doing? Factorial of 3. Okay, one second. Okay, there is this factorial of 3. When I call this factorial of 3, what is it doing internally? It is calling factorial of 2 as the first step, right? What is it again internally doing? It's checking if it is coming to the base condition. If not, it's calling factorial of 1. But factorial of 1 means it has come to the base condition. What is base condition saying? Whenever you call factorial of 1, you return the value of 1. Okay, that is a pre-computed value. Now, all the actual method calls are done, and as part of recursion, the second step is you return all those computed values to your calling function. Okay, now it's returning its value called 1 to the calling function. And what is it doing? What is the calling function doing? It's multiplying the returned value by its actual number. Here in this case, it is multiplying 1 with 2. And now this value is returning again, and finally it's multiplying, and finally what we are getting? We are getting the returned value to be 6. Right? This is what is internally happening inside a recursion strategy. The code, just by looking, will look very small, guys, but if you exactly don't know what's happening internally, then it's very hard to understand recursion. And believe me, if you understand recursion, then you can write big codes in very small number of lines. For example, in iterative approach, let's say you take so much big code, I'll tell you how we can reduce that in Fibonacci series. You write a little bit more code, and if you use a recursive strategy, the number of lines of code to be written will be significantly reduced. Okay, that makes the life of a programmer easier. But the important funda here is you need to understand how a recursion works internally, and only then you'll be comfortable to write that sort of coding, right? This is a small example that shows you how the factorial is internally working, correct? Let's move forward now and try to move a little bit forward now and try to understand what is our next thing. So our next thing would be, I told you initially that to any program that we write, we will be calculating time complexity and space complexity, right? Time complexity and space complexity. So at this point of time, it's not that easy to find out what is the time complexity straight away, right? It's not that easy to find the time complexity straight away. So let me give you one small formula for that. Okay, I'm giving you one small formula for that. So what is that formula? let's say in terms of recursive, when you need to find out time complexity, here's what it is. If it is a recursive one, I told you number of steps that we need to take. Yesterday we calculated the number of steps and we found out that the time complexity is order of n. But in recursive strategy, it's not that. It is what? The number of recursive calls that you are making. So what is the formula? The number of recursive calls that you are making and time complexity of each call. You are ignoring the recursive call. Okay, what is the time complexity of each call? Let's try to understand what this is. So here's it is. Now what I told you that for factorial of 4, what are the calls that we are making? First we are calling f of 4, that is calling f of 3, that is calling f of 2, and that is calling f of 1, and after that we are returning its value. Finally we are computing and we are saying the output is 24, right? The output is 24. But here what I want you to understand is we have taken how many method calls? The number of method calls are the number of method calls are, let me remove this. Okay, the number of method calls in our case is just 1, 2, 3, and 4. The number of method calls are f4, f3, f2, and f1, which is 4 method calls, right? 4 method calls. So, and is there any time complexity for every method call? Is there any time complexity for every method call? The only thing that they are doing in this method call is nothing, but you're not doing anything. You're just returning that. So as per the formula, we need to ignore this recursive call, right? Okay, let's ignore this recursive call, the time complexity of this recursive call, and see if there is any other function or any other loop which is taking more time complexity. And based on that, we need to calculate. But in our small program, we do not have anything of that. So the other than the number of recursive calls, we do not have any other time complexity here in this program. So that is why what we can conclude as per our formula is the number of recursive calls are 4 in our case, and time complexity of each call, which is nothing, which is order of 1. Let's say we are ignoring the recursive calls. So at this point, what we can conclude is the time complexity will become order of n, right? Order of n. So what is it? Order of n, because the number of method calls are 4. If the input is 8, the number of method calls are 8. If the input is 16, number of method calls are 16. It's like that. It's that simple. So this is how we derive the time complexity. So what I wanted to do right now is, let me try to fill up this table. We have taken factorial yesterday. Factorial is having a time complexity is of order of n. So that's what we saw in the revision. Here the space complexity is order of 1, right? And for recursion, just now we concluded as per our formula, the time complexity is order of n. Now we need to find out what is the space complexity, right? What is the space complexity? For space complexity also, there is a separate formula, guys. So what is that separate formula? Separate formula in terms of space complexity for recursive strategy is maximum length of stack and space complexity of each call. Maximum length of stack and space complexity of each call. I'll explain you what that is. Here in this example, what we did, we have calculated or we have concluded the number of function calls, right? So after it reaches function of f1, how will the f1 know that it needs to call f2? How will f2 know it needs to call f3? So there should be some mechanism internally, right? So what is that mechanism internally? I'll try to explain that to you, right? Let me put somewhere over here. So we are having 4 method calls, right? So what happens internally? Internally a stack gets created. Okay, internally a stack gets created. We'll be seeing more about the stack as we move forward in the data structures class, guys. But what is a stack as of now? Stack is nothing but a last in first out data structure. So which means, let's say you have some stack of plates in your home. So what you'll do, the lastly put plate you'll be taking, and after that you'll be taking the next plate. Whichever plate is at the top, you'll be taking it, right? Whichever plate is at the top, you'll be taking it. So just with that, what we have is we have a stack. Okay, we have a stack first what happens in our stack, there is a method called f4 which loads. F of 4 is loading. Okay, as part of our next call, we are loading f of 3. Okay, after that we are loading f of 2, and after that we are loading f of 1, right? So this is a stack. I told you in my first class, this is a stack, and every record that gets created for a method call is called as activation record. Okay, activation record. So this activation record is created for every method call, and what happens after you come until f of 1, you have reached the base condition of f of 1 says you need to return a value called 1 to it. So what it says, f of 1 should return a value called 1, and what it happens, the calculation of f of 1 is done. So what happens, the returned value is given back to f of 2, which is 1, and after that the activation record of f of 1 is destroyed internally. Why it is destroyed? Because its functioning is totally done. So now we have taken out the first plate in our stack. So what we have to do now, we have to go to the next plate kind of. So that's what we came to f of 2. What is f of 2 doing? F of 2 is multiplying the previously returned value by 2. So here what it is doing, 2 into the previously returned value is 1. So here this calculation is done, and now the activation record is destroyed. It's returning its value back to the calling function, which was f of 3. What is f of 3 doing? It is saying 3 into previously returned value 2, and now that function is also destroyed. After that, again its value is coming back to f of 4. What is it doing? F4 into 6, which is 24. So this is what it's doing. So finally, even this record is getting destroyed. So this is what is happening internally inside the physical memory of the computer. So here, let's not waste our time by understanding the internals, but the only thing that is to be considered at this point is, what is the height of the stack? As per our formula, what is the height of the stack? 1, 2, 3, and 4. Height of the stack is 4, guys. So when the height of the stack is 4, the space complexity formula, let's try to see that again. Space complexity formula says maximum length of stack. In our case, the maximum length of stack is 4, and space complexity of each call. What is the space complexity of each call? There's no extra space consumed, so that is order of 1. We are ignoring the recursive calls right now. What is the maximum length of stack now? The maximum number of length of stack is 4. Let's say your input is 20, the maximum length of stack would be 20. If it is 40, then it's 40. So which means it is proportionally increasing based on the amount of input, the number of input we are giving. So in this way, we can conclude the space complexity of a recursive strategy in Factorial is order of n, right? Order of n. We cannot see that as a programmer, what is happening. Just by seeing, we'll say, hey, nothing is there, there is no for loop, so the time complexity will be, the space complexity will be this, the time complexity will be this. So it's not like that. Internally, there are a number of function calls, and internally there is a stack which gets created, and internally this is how the method calls are organized. So that's why the space complexity will become order of n. Guys, you understood what I told, the explanation for calculating the space complexity? Please reply. We have taken a simple program which is factorial, and factorial is having only one line of logic. That one line of logic is 11. To understand this one line of logic, we need to have all that basics ready, guys, all these basics ready. So it's not that easy to learn these basics. Okay, I mean, I tried my best to make it as simple as possible. When you start reading computer science books, or when you start reading or some blogs, etc., they'll make you confuse more, and that then you will end up in learning either wrong thing or giving up in the middle. So it's not that. Recursive is very easy. I mean, recursion learning is very easy, but only thing is you need to concentrate. Even now, let's say you have a little bit of doubt. After you complete this class, you try to write the program on a piece of paper. Using this formula, you start calculating the time and space complexity. Once you become familiar with all these calculations and all, and believe me, any program that you are writing from now, you will actually know what you are writing, what you are trying to write. You'll actually know what is the space and time complexity you're calculating, right? Even when you go to your offices, even when you speak with your friends, colleagues, when you try to say, hey, the function that you have written is occupying order of n square time complexity, it's not good. And like most of people even don't know what that is, right? you will be having upper hand if you have all these calculations handy, and if you master these calculations, because this is very important, guys. This is very important for you to be a successful programmer, for you to be a successful employee as well, and to get the job in an early way, right? So let me just move forward to the next part. What is our next part? What is our next part for now? Our next part, let me open that. Let me open that. So what is our next thing? The final thing for today's discussion is Fibonacci series. So I'll straight away jump into the Fibonacci series program. Yesterday we saw what is a Fibonacci series program. The Fibonacci series, it starts with 0 and 1, and the next number will be a sum of 0 and 1, and next number will be sum of that and that. Like we have taken temporary variables a, b, and finally we calculated that to c, etc., etc., and finally we concluded what is Fibonacci series output. So when we try to solve the same thing using a recursive strategy, the number of lines of code will significantly get reduced to a single line of code. A single line of code that I'm highlighting right now to you. So what is it doing? It is calculating. For example, let's say there are numbers 0 and 1. The next number should be the sum of 0 and 1. So let's say there are numbers 7 and 8. There are the next number should be the sum of 7 and 8. So with this we come to a conclusion that the sum should be of Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? Fibonacci of n minus 1 and Fibonacci of n minus 2. This is what we have seen yesterday. For the people, let me just reiterate that again. So what is Fibonacci series? This is Fibonacci series. What is Fibonacci series saying? So Fibonacci series is saying the sum of 0 and 1 is equal to 1, sum of 0 and 1 is equal to 1, sum of 1 and 1 is equal to 2, sum of 1 and 2 is equal to 3, sum of 2 and 3 is equal to 5, sum of 5 and 8 is equal to 13. So at any particular point, for example, let's say you need to find the Fibonacci of 13, let's say. So what it should do, it should sum the previous two numbers, right? The previous two numbers, and finally it should return a value called 13. So which means what we understand, let's say there is a function called 5. So what it should do, so let's say the value of function called 5 is 13. How are we getting the 13th value? It's summing the previous two. So what is it saying? Function called 3 plus function called 4, function of 3 plus function of 4 will return me a value of function of 5, right? This is the easy understanding of it. So the same thing we are doing. For example, let's say 3 and 5, we are returning 8. How do we get to return 8? We are summing up the previous two function values, right? Previous two function values. The same thing is mentioned in the code as well. Same thing is mentioned in the code as well. So what is the code saying? It is returning Fibonacci of n minus 1 and Fibonacci of n minus 2, which means you're calculating the previous value with previous but one value, and you're returning that again to your calling function. So, right, this is a simple code, guys. Let me show that code to you and understand how it is working, right? How it is working. So this is the code, Fibonacci series recursive. Fibonacci series recursive. So if you see, this is the only
1 minute.
logic, only. Yeah.
Are you showing Eclipse?
Yes.
We are unable. Yeah, now only we are seeing. Yeah, go ahead, please.
Okay. Okay. Yeah, guys. So this is what it is. Let me show. So if we see, this is the only single line of code that we have written for Fibonacci series. Yesterday we have written a little big code, guys. This was the code that we have written. So what we have written, we have taken for a few variables, then we are trying to print something, then we are trying to write our logic inside the for loop, and then finally we are returning, right? All these things, all this code is taken care by a single line of code in recursive strategy. This is the only single line of code which is taking care in the recursive strategy. Internally it is creating its own variables, internally it's creating its own stack, internally it's doing everything, and finally it's giving us the returned value, right? This is how we have to write a program for recursive strategy calculation for Fibonacci series. Let me try to execute this program. Here we have given the Fibonacci series of 4. Yeah, okay, run as Java application. So what it says 3, right? So yeah, this is what it is. First one, it comes 0 0 and 1 plus 2, which is 3. So 1 2 3 4, this is our input, and finally it's giving 3, right? This is how it is. This is how we can write the program. This is how we can write the program. Now let's try to calculate. Previously we have done some exercise for factorial, right? For factorial. So let's try to do the same strategy or same exercise even for Fibonacci series program. I'll do one thing. Let me copy this and explain that to you even in a better fashion, right? I'm copying this for now. This is our simple code. This is our simple code, and let's move forward. Okay, so first what we will do, we will try to calculate the number of function calls that are associated internally, right? How it is, how the number of function calls are associated internally to our program. First, let me try to take something called f of 4. Internally, I'm taking the input as f of 4. F of 4, right? What is f of 4 doing? F of 4, for first Fibonacci of 4, we are calling n is equal to 4, right? So after these two are base conditions, if n is equal to 0 or n is equal to 1, then you either return 0 or 1. So f of 4 is not coming into these base conditions, so it will be coming to the return function. So what is the return function doing? The return function is calling f of n minus 1 plus f of n minus 2. So what is it first calling? It is calling f of n minus 1, which is f of 3. So what is 3 f of, so it's again the Fibonacci, there is a method call which is going, right? The method call again is going to the top, right? Again it's going to the top. So what is f of 3 doing? F of 3 is internally calling f of 2. F of 2 is internally calling f of 1. So what is f of 1 doing? F of 1 is a base condition. It's returning value of 1. So value of 1 is returned to f of 2. Now what is f of 2 doing? F of 2 is calling f of n minus 2. Now this is n minus 2. It is calling f of n minus 2, which is 0, right? Right? It is calling, it is returning. So what is its return value? The first, this return value will be 1, and this return value will be 0. And what is f of 2's values, guys? F of 2's value will become 1 plus 0. This is what it's doing here. F of 2's will become 1 plus 0, which is 1. Okay, this is 1. Now f of 2 is done with its execution. People are saying screen is getting stuck. Is it the same? Okay, so you are okay, you are able to see my screen. So let me start it again, so that becomes a fresh copy, right? That becomes a fresh copy. So what I have done one thing. That one thing is I'm calling f of 4, right? F of 4, function of 4. So this function of 4, what is it trying to do? It came inside here, and it is trying to see if it is coming inside any base condition. Please reply once. Okay, I'm repeating. I think you meant repeating. Okay, I'm repeating that from first. So what it's doing, let's say I'm taking an input called 4. I'm taking an input called 4. It's not coming to any base condition, so that is why it is coming to this return statement first, and finally it is calling f of n minus 1, right? F of n minus 1 is nothing but f of 3 in our case. So what is f of 3 doing? F of 3 is again calling f of 2, right? F of 2 is again calling what? F of 1. But f of 1 is a base condition, and it is returning a value called 1. Now it's returning a value called 1. That's fine. What is f of 2 doing again? It's calling n minus 2, which is f of 0, right? What is f of 0 doing? F of 0 is returning a value called 0. So what is f of 2 doing over here? The calculation would be for f of 2 is 1 plus 0, right? This is the calculation. So after that, f of 2 is done. Now the control is coming back to f of 3. So what is f of 3 doing? It's called f of 2, and after that it's again calling f of 1, because it should call f of n minus 1 as well, right? It is calling f of 1. So the control is near f3 now. So previous to that, f2 has even returned a value to it, f3, and after that f1 is completing its calculation. Because it's a base condition, it's coming back to f of 3, and now f of 3 is also done. What is it's doing now? The control came back to f of 4, but f of 4 should call f of 3 as well. So what is f of 3 doing? F of 3 should be calling f of 2. F of 2 should be calling f of 1. So f of 2 again should call f of 0, right? The control comes back to f of 2, right? Again, there should be call of f of 1, and since f of 1 is a base condition, it will be returning its value similar to how we have seen. And finally what happens, the returned value from f of 3 comes here. Okay, this is f of, just a second guys, I think I put f of 3 over here. Instead it should be f of 2, because f of 3 is already called, right? So in the second part, so f of 2 should be called, because f of 3 is already called. F of 2 should be called. F of 2 is internally calling what? It is calling f of 1. F of 1 is already a function which is a base condition, so the control comes back to f of 2 again. Now it is calling f of 0, right? It's calling f of 0. So with this, these two are base conditions, these two will be returning some value to f of 2. So after that calculation happens, and the control comes back to f of 4. This control comes back to f of 4. Finally there will be a sum of f of 3 plus f of 2, and finally there will be a returned value. In our case it is 3, right? This is how it internally happens. Internally what it is doing, it's trying to call f of n minus 1 and f of n minus 2. So if we deeply go into these calculations, guys, because of our base conditions, there are some cases which are left out. But if we see in a general case, let's say f of 4, it is calling in this way, and this again is calling in this way, this again is calling in this way, this again is calling in this way, this way, this way, this way. So what do you say? So with this, the number of method calls are becoming, number of method calls are becoming 2 power n, right? The number of method calls are becoming 2 power n. For example, let's say, what is the number of method calls here? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So the number of method calls are 15, right? Number of method calls are 15. In our previous diagram we are ignoring these two. The reason is we are calculating this in our base condition. But let's say the base condition is also not that properly defined, but the number of method calls which will be happening is 15, which is almost equal to 2 power 4, which is 2 power 4 is 16. So any number that you're taking, so let's say the number is 5, n is equal to 5, the number of method calls that happen is 2 power 5. 2 power 5 is 32 calls, right? For a small number which is 5, you are having 32 calls. For a small number which is 6, you are having 64 calls. For a small number which is 7, it is having 128 calls. You can imagine how exponentially all this get increased, guys, how exponentially all this get increased. So this is the number of calls that we are taken, and with the previous formula that we have defined, so what we have to calculate for, time complexity of a recursive function. With that, we finally concluded the number of function calls. Let me show you the formula once so that you will be even better understanding that. So this is, right, this is a formula that I told you. What is my formula saying? My formula is saying maximum length of tag into space complexity of each. Okay, this is space complexity. The number of recursive calls into time complexity of each call. The number of recursive calls, what are the number of recursive calls? Number of recursive calls are 2 power n, right? In our case, the number of recursive calls are 2 power n. So that is the reason our time complexity will become 2 power n, right? This is what we concluded. The number of method calls are equal to 2 power n, and then the time complexity will become 2 power n, right? Time complexity is 2 power n, which means it is the biggest time complexity. Please go through the chart that I have given initially, guys. The chart was something like this, it was like this, like this. There will be something like this, something like this. There will be an extreme case which is this, right? Extreme case which is this. This is m power n kind of a equation. So when you have equation like this is the worst ever time complexity that you can have, right? This is not a good way of programming, right? This is not a good way of programming. Even though it reduces the number of function it reduces our code significantly to a single line, it is not the great way of coding. But we can even improvise this coding by using a concept called memoization. We'll be seeing that as we move forward. But here what I want you guys to understand is, this is how we calculate the time complexity for a recursive program. So to calculate the time complexity of a recursive program, what we are trying to do, we are trying to calculate the number of function calls. The number of function calls we concluded are equal to 2 power n. So the time complexity will become 2 power n. Let's try to fill up our table. Here the time complexity for recursive of Fibonacci is order of 2 to the power 2 to the power n, right? So this is how the recursive is. Previously in our yesterday's discussion, what we have concluded, the time complexity is order of n. Order of n. The space complexity yesterday was order of 1, right? Order of 1. So with this, what we have to see, when you try to write an iterative program, it is doing with small time complexity, but it is taking more time complexity in case of recursive. But yes, we can improvise that, but let's see that in future. Okay, so with this, what we conclude is, even though the number of lines are getting reduced to significantly very less number in our program, it is having a bad time complexity. So a small program doesn't mean it's a good program, right? A small program doesn't mean it's a good program. Internally, it might create so much of effort, so much of disrupting, that the memory can increase so significantly, or the number of method calls can increase so significantly. So this is why we need to understand the actual basics of what is happening internally, so that you can write better coding, guys. uh, did you understand the calculation of time complexity for Fibonacci series in terms of recursive? Could you please reply to me? Yeah. So it's not n into n. So somebody has asked a question. What is that? One case, we have fact of n into fact of n minus 1. The number of recursive calls only, right? It's not n into n, right? The same thing. Let me try to tell that to you at this point only, so that that becomes very clear for you. So what have we done here in our factorial program? What have we done here? The factorial program, we have done only one thing. We are calculating the fact, and we are multiplying n. This is not something which is a function call or a method call, or it's nothing. It's like, for example, let's say you are multiplying that with 2, multiplying that with 3, and it has nothing to do with the incremental function calls, right? It's just a simple multiplication. So it will not become n into n, it will become order of n. Just see the formula once more. What I'm saying, you have to calculate the number of function calls, and after that you need to ignore if you take any time complexity in your factorial call, and ignore the recursive calls as well. See the formula once. Okay, I'll tell you what is the formula for that. So the formula for this is saying that the number of recursive calls for time complexity, number of recursive calls into time complexity of each call, right? Time complexity of each call, what are you doing? You're just multiplying your recursive call with a number. This doesn't take any extra time, right? It doesn't take any extra time. That is the reason the time complexity is only order of n. It's not n square. Okay, right. So now let's move to the final part for today. Final part for today is something like this. The final part for today is, we need to calculate for this piece of code, for the same piece of code. Let's try to calculate the space complexity, right? I'm just moving it. Okay, so what is the space complexity for now? Space complexity is nothing but we need to find the height of the stack. So how is the stack internally getting created? That is the question now. Let's see how the stack is getting internally created. So this is what the stack is. First, let's say there is a stack which got created like this. First, what it is doing, it is calling a function called f of 4, right? It is calling f of 4. So f of 4 is again calling f of 3, right? F of 3 is again calling f of 2, right? F of 2 is again calling f of 1. F of 1 is a base condition. So its calculation is done. Because its calculation is done, this activation record is getting destroyed. So since this activation record is getting destroyed, the control comes back to f of 2. What is f of 2 doing now? What is f of 2 doing now as per our number of function calls? So this is a function call. Let me move this, or I'll do one thing. I'll calculate it at this area so that it becomes visually clear for you. So what is it doing? First, we have taken a stack. Okay, we have taken a stack like this, right? What is the first call that's getting done? Which is f of 4. So f of 4 is calling what? F of 3. F of 3 is calling f of 2. F of 2 is calling f of 1. F of 1, there's nothing, is the base condition over here, so its calculation is done, right? Now the activation record is getting destroyed. The control comes back to f of 2. What is f of 2 doing? F of 2 is calling f of 0. Here there is a top available. I told you any insertion or deletion for a stack will happen only on top. This is top, right? So since this top is free now, we are calling f of 0 over here. F of 0, right? So we are calling f of 0 over here. What is f of 0 doing? F of 0 is doing its calculation. Finally, that is also getting destroyed, right? When f of 0 is getting destroyed, the control is coming back to f of 2. So f of 2, what is it doing? It is going back, the control is going back to f of 3. Okay, control is going back to f of 3, but before that, f of 2's calculation is also done, right? The control came back to f of 3. F of 3 is calling f of 1 now. What is f of 3 doing? F of 1. It is calling f of 1. So what is f of 1 doing? It's returning back to f of 3, right? It's returning back to f of 3. Now f of 3's calculation. So f of 1's calculation is done. After that, it's returning back to f of 3. F of 3's calculation is done. So the control is here now. The control is here now. The f of 3, now it is coming back to f of 4, right? It came back to f of 4. So what is f of 4 doing? It's calling f of 2, right? It's calling f of 2. It's calling f of 2. What is f of 2 doing? F of 2 is now calling f of 1, right? It's calling f of 1. So f of 1, its calculation is done. It's coming back to f of 2. Its calculation is not done. We need to call f of 3 as well. F of 3 as well. No, f of 0. This is f of 0. This is the one. This is f of 0, right? F of 0, its calculation is done. Okay. Now it's coming back to f of 2. What is f of 2? F of 2's calculation is done. Coming back to f of 4, its calculation is done. That's it. So with this exercise, what we have to find out is, I told you our actual motto of finding out is finding out the height of the stack. What is the height of the stack? 1, 2, 3, and 4, right? This is the height of the stack. So let's say when the input is 5, you start practicing. When the input is 5, how do you write the stack and how it is growing or what? And finally, you'll find the height of the stack is only 5. So which means the space complexity that is getting created internally of your RAM when you try to write a Fibonacci series program, or when you try to write a recursive program, a stack is getting created. A stack is getting created means an extra space is getting created. When your program is consuming extra space, then you need to represent that in terms of its complexity. So with this, what we concluded, the space complexity of our function call will be order of n, because what, our input is 4, the height of the stack that we got created is 4. So using this formula, what we can conclude, the space complexity is maximum length of stack into space complexity of each call. Every call that you are making is not taking any extra space. It's not consuming any extra space. It's just adding two recursive functions, right? It's only adding recursive function, and you're ignoring the recursive call. Like, I mean, if your recursive call itself is taking any extra space, you need to ignore that also. Only thing that you need to consider is maximum length of stack into space complexity of each call. The space complexity of each call is only 1, and the maximum length of stack is order of n. So that is why the space complexity of Fibonacci series will become order of n, right? So with this, guys, this is how we calculate the space complexity. Could you please reply if you are able to understand how to calculate the space complexity? Or just tell me if you are able to find out the number of function calls, or if you are able to find out how the stack gets created internally and how the method calls get destroyed. Okay, good that I got replies. So with this, guys, our agenda for today is complete. What was our agenda? Our agenda initially, as I told you, was to find out, our agenda for today was to find what is recursion. We understood what is recursion. We found a factorial program, a Fibonacci series program. We came to know that these are small lines of code. These are small lines of code, but at the same time, if we go dig deep into our understanding of what is happening internally to your system when you try to write a program, you found out that it's taking more space complexity, more time complexity. So that is why we can conclude, as of now, as of today, at this particular moment, factorial, not just factorial, the iterative way of programming is better in terms of space and time complexity in compared to in compared to recursive way of calling it. So, but yeah, as I told you, we can improve that as well. As we move forward in our course, we'll be seeing ways to improve the recursive strategy so that our code becomes less. At the same time, we are using the power of recursion. And as point number 3, what we did the complexity analysis. We were able to find out the space and time complexity for the programs that we have written. And with this base, you should be in a position to calculate the time and space complexity for any program that you